My name is Ruh Khurram. So I'll be sharing some examples, which is a composition of this CFD module within HPC 101, which is a very basic, very basic session. So we'll go through some examples, and before you worry about, well, should I make notes or should I replay the videos? Well, all the material is actually stored here. So I'll show you if I get time at the end of this session. I will give you a little bit of hands-on session on how to access this folder and how to run it, but only for Shaheen users. So external people, well, you need to first follow what Bilal mentioned, set up Shaheen projects, and then we'll be able to help you. Okay, so there are a host of applications, as my colleagues mentioned. I'm going to specifically just talk about CFD tools that are available. Of course, we can install more tools or codes that you are interested in, and you can also install yourself. So some of the notable tools readily available on Shaheen are Fluent and Converge. These are very popular CFD codes. Some open source codes like OpenFOAM, where you can actually start putting some solvers in there and then start playing with your own build as well. Then there is a code development tool, Deal2. This is a finite element method-based CFD framework in which you develop your own codes. Of course, you need to make the mesh. ANSYS is available for mesh generation. Normally, mesh generation is done on your laptops, and then you copy your mesh files and input files to Shaheen and then run. I'll show you all the workflow. Of course, when you're done with all the simulation, you post-process results, and then there is a tech plot, visit, paraview, and insight tools are available on Shaheen. So this is a cartoon of a CFD workflow. First, you start with a solid model. It is typically a 3D solid model, and then you mesh it. Depending on the computational domain, either you mesh it outside the model or inside the model, depending on if it is an internal flow or external flow. Then you send this data to a supercomputer, Shaheen, and where you run the governing equation, the numerical discretized version of governing equation. And once you are done with the simulation, your solution is converge. You post-process your results, and post-processing can either be done on Shaheen in a batch mode or on your workstation. Okay, so as Xiang already mentioned how to log in, so I'm basically logging into Shaheen. I'm putting my authentication. And you already know by now that you cannot run your jobs from home. So I'm going to project. You can also go to scratch, but in this case, I'm going to project. And I'm accessing the folder that I have already prepared. And then I'm going to a specific test case small. There's a README over there for you guys. You can look into it. It's basically a 3D cavity flow problem. There's some description there. And now I'm going to show you how to run this case. So you can see some folders. I'm going to a particular folder. I have all the input files available. You can look into the input file here. And now I'm looking at the job script, as Mohsen actually expertly described you all the details about job script. So this is, I'm not going to change, add anything here. So this is a standard job script. It's available for you, and you can run it. And just sbatch and job.sh will do the trick. You have submitted the job now. Now, when you're submitted, you need to know if the job is running or not. So you look at your job status by SQ. It's running. So once the job is running, it will finish. The job is finished. Now you want to visualize the results. On Shaheen, as Xiang mentioned, you don't visualize the results using interactive sessions. So we have to write scripts to visualize results. So this is a specifically prepared script using TechPlot. Those of you who are familiar, they are familiar, but it's basically a script that is using a post-processing tool to visualize the results. The picture on the top is the result that I have obtained right now, and this is a reference as the result. They are included in your tarball also. So now let's do a little bit of fun with this simulation. For some weird reason, if you want to change the physics of the problem, you can just open ANSYS, of course. You can go into the input file and you can change the physics. You can change the material models. So you want to simulate air or water, or you want to change the input boundary conditions. In this specific case, I'm actually just changing the flow on the top of the top wall of the cavity flow. So I'm going to open the input. This is my mesh geometry, a very simple thing, but of course you can visualize model very, very complex problems using ANSYS. So I'm going into the materials. It's air. Of course, you can change it, but in this specific example, we're not changing it. I'm going to boundary condition. I'm going to the top lid, and then I'm going to go and what do? I change the sign of the velocity. So it's basically reversal of the flow. Now I'm going to close my file, save it, and close the session. I copy this file to Shaheen, and again, of course, I run my post scripts to see if the solution has changed. So we can see that obviously the solution has been reversed here. So it's a nice way for those of you who are not familiar with running things on Shaheen or any supercomputer, how to play with it. All right. So now let's model something real. So let's say you want to simulate a flow over a sedan car. You want to reduce the acoustic effects or whatever. So here's an example. It's an external flow on a passenger sedan car, 4 million node problem. So I have everything ready. So I'm going to a 32 node case, which is a 1000 core case. I want to submit my job now. Once I this is a job script. Now you can see that now I have a 1024 processor job. So I'm submitting my job. I'll look at the status. Well, it actually gave me a job instantly, which is good. Now let's see if the output files are being written or not. Let's check it again. Oh, the job is finished. It's too fast. It cannot be true. So let's check the output file, and if we can see some problem. Oh, I can see there is a license problem. So we are exceeding the available license. So some of the software are seat based. So you need to be careful that at a given time, not many people are using. So I will run this case on a reduced number of cores, because specifically for ANSYS, it's a core-based license. Well, this is a very old tutorial, actually. Now we have increased this limit to 10,000 cores, actually. But this is just a proof of concept, just for you to be aware of certain things that can go wrong. So now I'm going to run it on 64 cores, submitted, and it's running, hopefully, and it will converge. And once it is converged, would like to look at the result. So I have all the scripts available. I'm just visualizing this result. This is a section view. So it's a half of car is simulated here because we are using periodic boundary condition. You can see the high pressure at the leading edge. So again, these are the analysis sometimes engineers use to reduce the noise of for the vehicle, just to increase your quality of drive. Good. So now I have given you a lot of examples. Some of you might be saying, well, why you have to come to Shaheen to do all of these things? You might be perfectly happy doing it in your laptops. So the reason is that you come to a supercomputer because you want to reduce the time to solution. Meaning, if you want to run a case that on your laptop, for let's say, let me take an example of this case. So this case is running on 32 cores, and it is taking 223 units of time. It could be seconds, it could be hours, it could be days, or whatever. If you throw more processor on it, it can be reduced to 10 seconds or 10 days or 10 minutes. So that's a massive gain. You really want to reduce the time to solution. And it's a very powerful thing. Here, I'm not showing just a small section of code that is scaled. It's the full simulation has been scaled. So this Shaheen and a scalable code actually gives you this X factor. So Bilal, can you please tell me how much time I have now for the hands-on session?
Well, you can go like you can have like a
I
1
have
minute.
2-3 minutes.
Yeah, 1-2 minutes. Yes. Go ahead.
Okay, I'll just go very quickly. So here is the tarball that you have. You can copy this tarball. I have given you the instructions there. I lost my connection actually. So I'll actually, I can stop right now. Basically, you just go to this tarball and then you read all the input files, and then you can run the session. I can try to log in quickly again. But you can stop me when I really get out of time. This is a good tutorial for you to see how actually things happen actually. So I go to this CFD module. I can see a case for Converge, Fluent, OpenFOAM, ParaView, TechPlot. I'm going to Fluent test case. I go to a test case small, which is a sedan car case. And then I'll look at it. I have different folders here. I have reference results here for you. I have some scripts. You can just run this script, and it's going to submit all the cases for you. Once you get the solution, you can get the report of your scalability results. Now you can see, now this is even better than what I showed in your results. So it's even at the 1000 core, it's perfectly scaling linearly. So once you get the solution, you can take your data files to TechPlot folder or OpenFOAM folder. All the scripts are available here, and you can visualize. You can just run job batch job.sh, you will get the picture. So with this, I'll let Bilal to talk about the programming environment. If you have any questions, I'll be happy to answer in the chat box. Thank you very much, Bilal. Over to you, Bilal.